My name is Sarah Kitten. I'm an undergraduate at the University of Oregon, and my research centers on webcam gaze-controlled screen magnification for low-vision users. I've been conducting this research with Jessica DeWitt, an undergraduate at Georgia State University, under the mentorship of Drs. Kristen Shinohara, Reynold Bailey, and Cecilia Alm, as part of the Computational Sensing for Human-Centered AI REU at RIT. Many people in the low-vision community are able to use their remaining vision to read text and navigate websites by using magnification software such as Zoom Text or the Windows native magnifier. The user can control the position of a magnifying lens using their mouse, allowing them to view small elements such as text without losing track of its context on the page. In our research, we wanted to investigate the possibility of controlling this lens with eye gaze captured by an ordinary webcam. This could allow a user to magnify any part of the screen just by looking at it, and without the need for mouse input or expensive eye-tracking hardware. Our research builds off previous research on gaze-controlled magnification. But because our study was entirely virtual and conducted over Zoom video conferencing, we built a new JavaScript-based magnifier using an API called Gaze Recorder that performs real-time gaze tracking without any special equipment or software. This increases the practical value of the system compared to previous research, because the user does not need an infrared eye tracker, just any built-in webcam. In our work, we examined the following research questions. How well can webcam-based gaze tracking capture the gaze of people with low vision? How can webcam-based gaze tracking be used to control the movement of a screen magnifier and decrease the need for a mouse? And how effectively can people with low vision complete reading comprehension and target acquisition tasks using a screen magnifier controlled by webcam-based gaze tracking? We conducted our research in 3 stages. We began with formative testing with low vision subjects who completed reading comprehension and target acquisition tasks using a preliminary version of our magnifier, which was controlled by the mouse. We used the iMotion's online data collection module to collect gaze data, and we recorded the speed and accuracy with which they completed the tasks. Next, we developed the prototype for the JavaScript-based magnifier that moves based on webcam gaze tracking. We incorporated observations from the formative study into the improved methodology and gaze tracking magnifier used in the summative study. Finally, we conducted summative testing with low vision and corrected vision subjects who performed the same tasks as in the formative testing, but with the new magnifier and some changes to the methodology to make the experiment run more smoothly. We recorded gaze data as page coordinates, and again recorded the speed and accuracy with which they completed the tasks. These 3 stages build the structure of our research. The primary value of the formative study was to test the foundation of the JavaScript magnifier, to test our implementation of the visual tasks and how participants responded to them, and to identify problems with our system and methodology and ways to improve it. Out of the 6 formative study participants, we were able to collect eye tracking data from participants number 2 and 6. iMotions indicates that this data has eye tracker accuracy ratings of -1 and 0, and data quality ratings of 0% and 98%. This preliminary information, which is limited due to several technical difficulties, indicates that webcam eye tracking may often or always have low accuracy for people with low vision, and that the quality of eye tracking data samples may be highly variable. Although the results weren't very promising for the idea that webcam gaze-controlled magnification would be usable for people with low vision, the formative study allowed us to test and troubleshoot the difficult logistics of the remote study and the target and reading tasks, and gave us useful information that we incorporated into the gaze-controlled magnifier for the summative study. We found that although we allowed participants to request that the magnification strength be increased or decreased at the beginning of the study, some participants were still unhappy with the size or magnification strength of the magnifier. This prompted us to implement controls in the summative magnifier that would allow the user to customize the magnifier themselves at the beginning of the study and at any point throughout. Also, due to the low observed gaze tracking accuracy and the difficulty of finding participants with low vision, we decided to expand our recruitment for the summative study to include people who have vision corrected to 20/20 with glasses or contacts, by asking them to participate without correcting their vision. To test our gaze-controlled magnifier, we recruited low vision and corrected vision participants to perform 2 tasks using the magnifier while sharing their screen on Zoom. First, the participant is given a link to the web page hosting the task, and asked to set the size and magnification level of the magnifier to their preference. Next, the participant sits comfortably in front of their webcam and follows a moving dot with their eyes to calibrate the gaze tracking. The first task was a target acquisition task. After calibration is complete, the participant is given 5 minutes to complete the task of finding on each image the button that says Next as quickly and accurately as possible. The second task was a reading task. After again setting up and calibrating the magnifier, participants were asked to read 2 passages, answering a comprehension question after each passage. For both tasks, we recorded the magnifier configuration, the time spent on each subtask, and a log of the participant's gaze coordinates. Currently, we have task completion data for 7 participants. Here you can see a representation of the time data we collected and compare the performance of these participants on the target task. The y-axis shows the number of next button subtasks completed by the participants, graphed against time on the x-axis. The numbers on each line correspond to the participant ID. We are excluding the data from participant 4 for this task because of technical difficulties. The success of participants varied significantly. Participant 6 was the only participant to complete all 11 subtasks, while participants 2, 7, and 3 completed less than half. Subtask completion tended to taper off around the end of the time period. This might be due to fatigue or frustration with the task, or to increased difficulty as the magnifier became less accurately calibrated over time, and participants became more likely to try less effective methods of moving the magnifier, such as with head movements rather than eye movements. Here you can see a similar representation of the time data we collected for the reading task. We are excluding the data from participant 6 for this task because of technical difficulties. For this task, subtasks 1 and 3 are the paragraph reading sections, and subtasks 2 and 4 are the multiple choice questions. There are not significant similarities in comparative performance for individual participants across tasks. Participants 2 and 7, who were some of the slowest performers on the target task, are among the quickest on the reading task, completing all 4 subtasks, while participants 1 and 5, who were among the quickest performers on the target task, are among the slowest on the reading task. One possibility is that participants who did well on the first task were more likely to be complacent during the calibration process for the second task, while participants who struggled due to poor calibration on the first task were more likely to focus during calibration for the second task. All of the participants we were able to collect data from had vision corrected to 20/20, except for participant 5 who had low vision. Note that participant 5 performed the target tasks more quickly than most, and also performed quickly on the reading task. This participant may have been more invested in the possibility of the system for their personal use, and more accustomed to the use of screen magnifiers than the corrected vision participants. Although we do not have statistically significant numbers of low vision participants, it is promising to see that our magnifier may work well for at least some people with low vision. In addition to task completion times, we collected survey data indicating cognitive load and usability, which Jessica will be discussing in her presentation. We also collected data on the size and magnification level chosen by each participant, which we may later test for correlation to task performance, and a log of each participant's gaze coordinates for each task, which we may later analyze to gather more data on the paths each participant took to move the magnifier to different elements on the screen. This study was subject to a variety of limitations and technical difficulties. Because each participant participated on their own computer in their own home, there was little we could do to standardize video quality, lighting quality, screen size and quality, the distance from the participant to the screen, or the participant's internet speed. Of course, these irregularities also serve the ecological validity of the study, which aims to examine the effectiveness of an eye-tracking screen magnifier that could be used outside a controlled environment and without special equipment. Many participants didn't show up to the study, many did not have sufficiently good internet or video to use the magnifier, and many were unable to have their gaze register with the program because of their low vision. Our observations so far indicate that current webcam-based eye tracking is probably not usable for most people with low vision, and is limited by time-consuming calibration procedures and the need to remain still and well lit. However, improvements to the gaze tracking API could potentially help with some of these problems. Improvements to the calibration system, such as post-calibration adjustments and calibration save states, could make the system more practical, and options such as only tracking the movement of one eye could make it more usable for people with one eye that is more functional than the other. Future research could look into these possibilities and into other ways that computer vision could be implemented as an eye tracking system for people with different vision impairments, and how it could be implemented into a usable accessibility system. Our formative study provided information related to our first research question, indicating that webcam-based eye tracking may have similar problems to infrared eye tracking in its inconsistent results for people with low vision. Our second research question led to our technical contribution of a fully web-based gaze tracking magnifier that uses the Gaze Recorder API to control a JavaScript magnifier without any special equipment or software downloads. We found that webcam gaze tracking could be used to control such a magnifier. However, our third research question needs further exploration with more low-vision participants and a more accessible gaze tracking API. In this work, we worked with webcam-based eye tracking to develop and test a gaze-controlled screen magnifier. We think that our work can serve as an initial exploration of the capabilities and limitations of this technology, and lay a foundation for future improvements that could improve its utility for people with low vision.